Hey folks, here is a video answer key for this review. Alright, so the first chunk of problems really easy. It's really just checking if you know what these words mean on a graph. So the first one's x-intercepts, just where your graph hits the x-axis, they're circled. Y-intercepts, where your graph hits the y-axis, there it is. Relative max, that's the highest point. It's like a hilltop. It's not the highest point of the whole graph, but relative to this area it is. And then relative mins, there's two of them. There's one there and there. And you're supposed to write them all as coordinates. That's not too hard. This next chunk, what is not a polynomial? Well, polynomials have to have real numbers in front, and they have to have exponents that are positive whole numbers. So this guy's cool. Real number, no imaginaries, and positive whole number exponents. There's a 1 there. Doesn't say. So that one's cool. This one fails because I is imaginary, so that one's not a polynomial. Alright, and then the next one's cool. Whole number, real number, that's fine. This one fails because that radical x is like writing x to the 1/2. And you're not allowed to have fractional exponents, so that's not okay. This one's okay. This one fails because you're not allowed to have x's in the bottom, because that's like an x to the -2. Let's see, this one's cool. Even though they're decimals, they're fine. What's not okay is this. Because you're not allowed to have decimals in the exponents. They have to be positive whole numbers. So we had 4 of them fail that are not polynomials. Down here, the degree is the highest power in x, so degree is 4. And the leading coefficient is the number in front of that, so -5. Likewise, be careful here. The degree is 5. This one's not in standard form, so sometimes you got to be kind of careful with that. And this one, a little bit sneaky. Degree is 1. There's a 1 there. And leading coefficient, there's also a 1 in front of it. Alright, so moving on. The next chunk of problems wants you to write the end behavior. And end behavior is what your graph does way out at the edges. In every one of these, you can set, oh, I had a typo. This should be a negative in front of there. In every one of these problems, you should set them up ahead of time. So I'm going to pause this and set up the problem. So here's all the setup work. And basically, this says as x goes -infinity, so as x goes left, what do my y's do? And if you look at the first term, these don't matter. If the power is even, it either looks like this. So here's what even powers. It either looks like this in the end or this. If it's positive, it looks like this. If it's negative, it looks like that. And then odds, odd power, either looks like this if it's positive, or this if it's negative. So you look at this, even power and positive, both my graph goes up and up. Now I got to be able to say that in math terms, which is as x goes left, what's it do? Goes up forever. Guess what? I got a math number for that. There's up forever. As x goes right, looks like this, goes up forever. Positive infinity. Okay? Then we go here. Remember, I don't care about the number in front. Is the power even or odd? The power is a 5, so it's either going to look like this or this. Since it's a negative in front, I know it looks like this to the left and this to the right. So as x goes left, that's what negative infinity means, my graph looks like that, which is positive infinity. As my graph goes right, it looks like this, which is down forever. Okay, similarly, here's an odd power, but positive in front. So odd power, positive in front looks like this. and it's going to go down, up. So I have negative infinity for the left, positive infinity for the right. And last but not least, you have even power negative number. An even power negative number goes down, down. So down is that, down is that. Two answers. Sweet. That's called end behavior. Remember, only the biggest power matters in that. Usually all the numbers matter, but not this one. All right, so now we're going to switch gears and talk about even, odd, or neither. Algebraically, how do you show if a function is even, odd, or neither? It doesn't matter about the numbers in front. Algebraically, if you plug in a number and the opposite number, you look at their answers. So if I get a calculator out, I'll type both these in. All right, so I plugged in a 2 and I got an 18. I plugged in a negative 2 and I got negative 10 to that equation. And if those don't match, your answer is neither. And if they did match, if it was like 18 and 18, it would have been even. And if the numbers matched but the signs were different, like 18 and negative 18, it would have been odd. So let's try, okay, I could do that here, but this one said, how could you do it graphically? So you type this in your graphing calculator, and I'm going to sketch what it looks like. It looks something like this. And if my graph is symmetric to the y-axis, which this one is, it is even. If it was not symmetric at all, it would be odd, and if it, it would be neither. And if it was something like this, it would have been odd. So that's an odd one. But that's not this problem. This problem looks like that. All right. I could have also done this thing and they would have come out as the same number both times. All right. Adding, subtracting. I'm going to do these off screen and just write the answers because you guys should be able to add these. All right. Here's adding and subtracting. You should be good at that. Just don't forget to distribute the negative before you combine like terms. All right. Now to the back. Okay, multiplying, you should just make sure every term in the front multiplies by every term in the back. 6 times 2 is 12, x to the 5th plus 18x squared. And then I make sure everything here, negative 10x to the 3rd and minus 15. And then you see if anything else combines. I should probably rewrite this in standard form, which would be to put the highest power first, the next highest power second, and then so on. This would be a better version of the answer because they're in order. I guess the directions didn't say it, but really it's a good habit. Same deal here. You're going to take this to all three of those. So you're going to go 4x to the 6 minus 8x squared and then plus 32x. And then you're going to do it again with this guy. We're going to go 3x to the 5th minus 6x plus 24. When I look at all this, I think only these two combine. So I'm going to rewrite it in biggest one first, 4x to the 6, right? And then that's that guy. And then we got a 3x to the 5th. And then we got a minus 8x squareds. Then we can put these two guys together. That'll be plus, what is that, 26x and then plus 24. Just make sure you don't miss any. Okay, cool. Now we're getting down to the end here. Here's synthetic division. Love synthetic division. So remember, synthetic division, first thing you do is write the number with a different sign. So even though it's x plus 3, I'm dividing in a negative 3. Change the sign of that guy. And then second, you just steal the exponents, but be careful, or not exponents, steal the coefficients. Be careful you don't miss any. So this is the x to the 3rd column. This is the x squared column. This is the x column. And this is the ones column, or the constants. So I didn't need any placeholders. And then I drop my first number, and I multiply and add, multiply and add, multiply, which is 34 times negative 3 is negative 102, and then add 5 and you get negative 97. So remember how to reinterpret your answer. That's your remainder. Okay, so what do I do with a 3? Well, I stole all the x's from it. I got to put x's back, but it goes down a power each time. So this is actually, if the beginning start is x a third, this one is how many x squared you have. So 3x squareds minus 11x's plus 34, remainder negative 97. Or if you want to get fancy, you could say remainder negative 97 over x plus 3. That would be really cool. But you don't need to do that. You can just say r negative 97. All right, similarly, this one's a little sneakier though, because I don't know if you noticed, but after I put a 2 out there, I put a 1 here for the number in front of this. Did you notice there's no x squared term? You got to put a 0 placeholder. And then a 5 for the x's and a negative 1. Watch the sign on that. So I drop the 1, multiply, you get a 2, add. Multiply, 2 times 2 is 4, add. Multiply, 2 times 9 is 18, add. There's my remainder. So remember, if I started with cubed, this is how many squareds I have. So I have x squared, you can say 1x squared if you want, plus 2x, plus 9, remainder 17. Or if I want to be really fancy, it's 17 over that. Sweet. All right, one more chunk here, and that is, do you remember all these special names? So if you see the highest power, I'm going to say the degree and classify the polynomial. So this is a quadratic, because the highest power is 2, and since there's 2 terms, binomial. Quadratic binomial. Fancy name for it. What's the fancy name for this? Well, if the highest power is 3, cubic, and 1, 2, 3 terms, trinomial. And then, if the highest power is 1, which it wasn't right there, it's called linear. And if there's 1 term, monomial. You can mix these up and have like almost any combination possible. And then lastly, if you see the highest power is 10, that's higher than any special name, right? You're supposed to know these 3 special names. Anything higher than them, you just say a 10th degree, and I have a special name for single term, that's monomial, double terms, binomial, triple terms, trinomial. After that, we don't give it a special name. We say there's 1, 2, 3, 4, 5. A 10th degree, 5-term polynomial. That's the fancy name for it. All right, so hope that helps. Good luck. Talk to you later.